It's coming. Okay. Thank you. Thank you very much. I would like to thank also the organizers for the kind invitation to participate in this symposium and deliver this lecture. Thank you very much. And I would like to present what I call the micromorphic approach to gradient plasticity and damage. This is joint work with my colleague Mathieu Mazière from School of Mines in Paris, and my former PhD student Özgür Aslan, who is now in Ankara. In fact, I will start by motivating this micromorphic stuff by some physical consideration coming from strain localization phenomena. I will give some examples. And then I will present the general framework that you can use and apply to your favorite models, in fact. And I will apply then to strain localization for metals here. Especially I will concentrate on the modeling of the propagation of Luders bands in steel. And then the last part will be dedicated to damage, so I will call it the micro-damage model, because it is based on this micromorphic approach. And we will simulate the propagation of cracks in single crystals, also with a view to application in nickel-based superalloys, in fact. Okay, so I start with these tensile curves of standard steel. In fact, that here this is a steel used in nuclear industry, but you have many curves like this, which, for instance, at room temperature or even lower temperature, if you have a zoom here, you see that the yield stress is somewhat complicated because you have a stress peak here, you have a stress drop, you have a plateau, and then you have some hardening. Usually in engineering, you try to circumvent this by smoothing below or above. This is a choice that you have to make. But here we will try to take this into account in the modeling, in fact. So this is, in fact, known as the Luders phenomenon. I should say the Piaubert-Luders phenomenon, because there was a French guy before, of course, as usual. And in fact, they're characterized by this plateau stress here. And if you use some image correlation and strain field measurements, you will see the reason for this plateau and peak stress. In fact, you will see that the strain is not homogeneous. It starts with some localization here, about 2% here, and you see you have two band fronts here. So you have a front here and a front here which propagates until the sample is full of this plastic band, in fact, and then you have standard hardening. And in fact, here this was axisymmetric samples with a circular shape, so that the bands, in fact, also turns a bit when it goes along. And this you find if you plot along the axis of the sample, if you plot the plastic strain or the total strain that you measure here, and you see that at the very beginning you have a bump here, which is the localization of the band, and then the band will propagate. And you see the front, there are two fronts here, the band propagates, and the irregularities are due to the fact that the band is not nice and goes like this, but it rotates a bit, and the field is a bit more complicated than in a plain samples, for instance. And you have a clear definition of the band front until you have some homogeneous strain at the end, and you see that there is a specific size of the band front. It's not a discontinuity, it's something which has a definite thickness that you can measure by strain field measurements. And if you try to simulate this, it is done a lot in industry also, usually to simulate, especially in steel industry, of course, what you do is you take a constitutive law, which is this dotted line here, where you have softening and then hardening. The softening will induce localization, and the hardening will induce propagation of the band, in fact. And if you compute on a volume element, you get this constitutive curve. But if you compute on a sample like this, you will have a stress drop here, and then a plateau. And what we observe, and people usually don't really care with the mesh of the finite element method they are using, because they think that due to the hardening that comes at the end, there will be no mesh dependence. But in fact, if you look more carefully, you see that if you choose a regular mesh, if you choose a random mesh, already the plateau is a bit ugly and not really reproducible. But if you are nasty and you want to align the elements parallel to the localization band, because you can predict the orientation of the band, then this is a nightmare. What you get is this very strong curve. It has nothing to do with the experimental curve, in fact. This is due, of course, to the discontinuity and, of course, the propagation of the band here. So there are some artifacts related to the mesh. When you do such simulation, you have to take care of that. In fact, this phenomenon is also present in porous materials, not in the form of Luder's band, but in the form of crushing bands. For instance, in these aluminum foams, which you can observe by X-ray tomography. And what happens is that if you compress it, you will not have homogeneous deformation. You will have a crushing band here. This time the band is not inclined, it's horizontal, in fact almost, due to the crushing of the cells here. And it will propagate until you have fully crushed all the cells, in fact. And this you can model by plasticity, compressible plasticity, very simple model that we used at that time, based on an elliptic criterion, in fact. You can even calibrate the parameters if you look at the contraction inside the bands by the field measurements. So you can calibrate the ratio between the part due to the trace and the part of the deviatoric part. And you can simulate the phenomenon, and you have the propagation of crushing bands like this. And at the end, you have again some hardening due to the crushed cells. And again, you observe this oscillation in the simulation. So we have found now two motivations for introducing some higher order theory and length scales in the landscape. Why? First, because we have found some mesh dependency in the results. So if we want to trust the results, we have to regularize. So we need this length for that purpose. And second, we know that there is a length scale in play in this phenomenon in the thickness of the front band in the Luder's phenomenon and in the thickness of the crushing band related to the cells in the foams. So we want to bring two concepts in the same length, in fact, and this is what we will do with the second part here, where we will try to introduce characteristic length to account for these effects. Okay, this is, first I have to say a few words about micromorphic. What does it mean? Where does it come from? So it comes from the golden age of the new continuum mechanics, where Mindlin and Ehringen wanted to introduce microstructure effects in elasticity, mainly, in fact. And Ehringen coined the word micromorphic. And in his idea, in fact, it was related to the fact that in the microstructure you can have some specific physical directions which are not necessarily material directions, so they don't follow the deformation gradient, but they are evolving, so they are stretched and rotated by a micro-deformation tensor. It means a full general second-order tensor without any symmetry at the with the property that this field is not necessarily compatible because it is not related to the material deformation, in fact. So this is the origin of this word, and it was then used also by Germain when he formulated this theory based on the method of virtual power, and this is the methodology I will use, and even he extended the micromorphic deformation to higher order tensors, in fact. And what I am doing now is extending this approach to other variables that this full second-order tensor, simply to strain-like or a hardening variable which may be tensor or scalars. So in some sense, I am extending the approach and also simplifying it, because you don't necessarily need the full second-order tensor, which is, of course, very expensive in computation. We may reduce to scalar quantity, and this is what I will do in the rest, in fact. So now the generic approach is the following. Simply, you take your favorite model, which displays some problem of mesh dependency, or in which you want to introduce some characteristic length. So let's take an example related to plasticity. So we have the displacement degrees of freedom. We have the elastic strain tensor. I will stick to the small strain framework for simplicity here. And we have, for instance, the cumulative plastic strain variable. You may have additional hardening variables, for instance. What I am doing is I extend this set of degrees of freedom by an additional quantity, which I call here pchi, so which I call the microplastic variable here. There is a p, meaning that it will be related to plasticity, and there is a chi because it's micromorphic, in fact. And not only the variable, but also its gradient is introduced in the set of internal state space, in fact. And what we are doing, following Germain, in fact, we are extending the power of internal forces. So this is the standard virtual power of internal forces with the Cauchy stress tensor here, the strain weight tensor. And I add a linear contribution with respect to the micromorphic variable and its gradient here. And I do also the same at the boundary, so we have to introduce generalized contact forces, also this is necessary. And then I state the principle of virtual power here, in the static case here, where we will equilibrate these internal and applied forces. What you get, because you have two sets of independent variables, remember, they are independent degrees of freedom, the velocity and the plastic, microplastic variable. So you get two equations, two balance equations. This one, the standard ones, where I excluded volume forces for sake of brevity here, and this second one, which give a relation between the generalized stresses small a and small b here. So they are related by these equations. You have the corresponding boundary conditions, so generalized tractions, would say. And if you have a free boundary, this traction will vanish. But inside, of course, if you have a cut, they will not vanish. I recommend to read also the work by Sanouni, who also added some dynamic terms, which I did not do. Why? Because he wanted to extend it to explicit simulation, so you need the full equation. So you can look in his book also, this is explained. Now we want to formulate the constitutive equations, and if you look at the formulation, there is no change compared to what you know with the internal energy density here, the heat flux, there are no changes. I will discuss first plasticity, so the split in elastic and plastic strain. And where are the changes? The changes are in red. They are in the constitutive functionals for the free energy function, the stress, the higher order stresses, and the entropy. And if you plug this into the Clausius-Duhem inequality, you see this new contribution. Here you have the plastic power. Here you have the energy stored by hardening, for instance. And here you have elasticity. And now what I will show you is the most simple example. I will make the assumption, constitutive assumption, that these terms are non-dissipative. So the most simple case, purely reversible laws for this higher order traction. Of course, if you want, you can add some dissipative terms, but I don't need them for the examples I will give today, in fact. And then you have new hyperelastic relationships, these new relations, where you take the derivative with respect to the micromorphic variable. If you look at the residual dissipation, there are in appearance nothing, no difference, but it will come, of course, in the partial derivative. So let's have a look at the choice of the free energy function. I propose a very simple extension of the classical model by quadratic contributions, quadratic in the gradient, and quadratic with respect to the difference between the plastic strain and the microplastic strain. So this is the place where I give some meaning to this higher order degrees of freedom. Now, the microplastic strain is linked to the plastic strain itself. In fact. And this modulus here is a higher order modulus, can be interpreted as a penalty term which penalizes this difference here. Now, if you take the derivative of this free energy function with respect to P, in fact, you will have new contribution in hardening. Here you have H. I have taken a very simple case of linear hardening. So you have linear hardening, but the law is modified by the new contribution. If you plug the constitutive laws into this new balance equation, you end up in the isotropic case with a very simple equation, this one, which is well known. It's a sort of regularization equation, which is now derived from the constitutive functionals, in fact. You have an intrinsic length coming in by the ratio of this A here, parameter, and this penalty term. Okay, let's give an example, plasticity. So strain gradient plasticity, how do you get it from this? You take a yield function with some equivalent stress here. You look at the radius of the plasticity locus here, and you have new hardening law here. And then you can, you assume you have plastic loading, for instance, here, and you see the difference P minus P chi here. You can take it from this balance equation, and you see that now, in your hardening law, you have a Laplace operator. You can compare to the well-known Ifantis model here, where there is a Laplace also, but the Laplace on the plastic strain in this very old and still useful model. So simply, you have to take the limit when h chi goes to infinity, so you put some internal constraints. Then this model will provide the Ifantis model. So this is a way to compute with Ifantis model by means of the micromorphic approach. The consistency condition is very easy in that case. So this is very micromorphic plasticity is much simpler than strain gradient plasticity. There is no need for a front tracking of the plastic domain, for instance. The variable is defined everywhere, and you see that the plastic multiplier can be computed from the strain rate and the microplastic rate also. Okay. We could say, why use thermodynamics for such regularization purposes? Why is it useful? I think this is an example where we really need it, because you could use instead mathematical computational heuristic method. You say, I want to regularize, so I put some mathematical operator. And then you can say, as was done in the past in the literature, okay, I have a new variable here, a sort of non-local variable, and I will substitute this new value into the hardening laws, for instance, simply in a heuristic way to modify the law. And if you do that, it has been discovered that you end up with ill-posed problem, and the regularization is obtained only in the case of softening and hardening materials are hard to work with in that case. Why? Because, in fact, we cannot. In fact, the free energy function which is behind is not positive, definitely positive, in fact. And this is the problem. So with the thermodynamics, we ensure that we will regularize the problem, in fact. And thermodynamics is for temperature, so if you have temperature dependence, you will see that the regularization equation is not simply this Laplace function here, but you have to add thermal contribution, and they come from the thermodynamic formulation. Okay, let's use it now. So we use it for Luders, and you see if we apply this micromorphic approach, which in the case here of high constraint is the same as strain gradient plasticity, the same as Ifantis model here, then you have no mesh dependence anymore. You remove the effect of the small square, the triangle, and so on, with a characteristic length, and you have the propagation of a front. In fact, you can, you see the front here in the computation also, which has a finite thickness, which you can calibrate on the experiment. In fact, this is how we calibrate the intrinsic length. In fact, you can get some analytical solution to check your finite element code especially. But then you take simply a softening hardening law here. And then I will skip the details of the computation, but we take the bifurcation band here, and we compute the profile of plasticity and in the zone of the front of the band here. And you say that there are two zones. There is a zone in the front of the band where the material is softening, and behind it is hardening. And if you solve the differential equation here, you will have a sinus function here and an exponential function here. You have condition at the interface of continuity of microplastic strain and of the higher order tractions. They are also continuous, and this gives you the profile. Okay, so you can also compute the plateau stress by Maxwell rule, so this is easy. And then you check your code that the front band here, this is a strain rate, that it's in accordance with the analytical solution. I would like to give application of the same model not only for tension, that I've shown at the beginning, but for shear also. Because if you do some shear of a metal strip in steel, you will have also propagation of Luder's band. And you see in the image correlation analysis, you see that the bands start at the grips, and then they propagate and they invade here. And again, you see the front. At the beginning, no plasticity. Then the plasticity starts at the close to the grips, and then the front and invades the whole sample. And this we can reproduce. Again, if you don't use the regularization, you have some spurious effect depending on the mesh you are using. And you have strange behavior in the simulation. But if you use the micromorphic model, then you have smooth fields, and you can calibrate, again, your length, which in fact is very close to the one for tension. The material was not exactly the same, so it's very close, of this order of magnitude, some hundred of grain size, in fact, from the slope, in fact, the maximum slope that you have in the gradient. You can really calibrate this. Okay, and I would like to switch from plasticity to damage. This is the next step. And with a very difficult situation, the one that you encounter in single crystals, and we have examples of that in application. I mean, if you consider turbine blades in jet engines, you have nickel-based superalloy single crystals, and there are cracks there, and you want to know how they will propagate. Here you have a crack in a CT specimen of single crystal, and this is the experiment here, and you see that there are slip lines, so we can really use crystal plasticity to predict the plasticity in front at the crack tip, in fact. If you perform some cycles now, so fatigue, in fact, you will observe the very complicated propagation of the crack. So this is really a nightmare. The crack front was here. You have first some bifurcation, you have some branching, you have hesitation of the crack, and mainly this zigzag progression. And if you look at the planes here, they are crystallographic planes. So in some sense, we are lucky because in this anisotropic damage model that I need, I know, in fact, the list of possible candidates for the cracking, in fact. And these are the 1-1-1 planes. And this is what I will consider in the model. I will consider that the strain rate can be split into elastic contribution, crystal plasticity, standard ones, but also damage strain. What do I call damage strain? Simply the possibility of opening strain, like this, along a plane with normal n here, meaning that you have some cracking and you have some volume changes because there will be some cracks inside which opens here. And you also have to add some accommodation openings here, in fact, mod 2 and mod 3 openings that you have in the model. And the main driven one is this one, which is in some sense the cleavage cracking on this plane. Okay, for that purpose, I use driving force, which is the normal stress to the crystallographic 1-1-1 planes. And if you reach a threshold, then I will start the damage law. But take care, once it starts, I have some linear softening, so the damage will localize, because in these single crystals, you don't have diffuse damage. You have localized damage and a crack, as you have seen on the pictures, in fact. So this is done by this softening here, which will promote localization into a crack, in fact. And the threshold depends on the accumulated slip and under cyclic loading, for instance. You have to take care because at the crack tip you may have opening, but you may have closure also. So you have to take care of some unilateral effects. And this you can do in that way. For instance, imagine you take a row of elements here, and you pull on it, and it will break. And now it's broken. I have taken an example of pure brittle case to illustrate. So this element is broken here. So you can pull on it like this. There is no stress anymore. And then you can shuttle a bit the sample because it's dead. In fact, you should have no forces. So this you can check in the model by the other forces, in fact. And so in the other side. And then you come back, and then you can compress it to close the crack. Okay, let's close the crack like this. Okay, so we come back here, and then we can go again into the elastic regime. So this is coded in the damage model that we have here on each of the 111 planes, in fact. So let's use it. So now elasticity here, and even plasticity if you have too much compression. Okay, if you use this damage model, this anisotropic damage model, in your finite element simulation, what you will get is mesh dependence, of course, as usual. If the mesh is coarse, the crack will propagate straight. If the mesh is fine, the crack will branch. Who is right? In fact, we know that the branching is observed. We have seen it in the experiment. But yes, that's why we need the micro damage model for that, to regularize these simulations here. Okay, so this is the simulation with the gradient damage model here. Oh, I should say which gradient we take here. I forgot to say that. So what I call damage here is not a variable between 0 and 1. This is a sort of strain, in fact. This is an opening strain, if you want. So it can vary up to infinity if you separate the two parts. Okay, so this is more a strain than a damage in the usual sense. And I take a scalar variable, and as usual with the micromorphic method, I introduce some micro damage variable decay here, and the gradient and so on. Same, again, only one additional parameter. Okay, so I applied this on this crack here, and this was done by Özgür Aslan and Prajval Sabnis more recently. And you see, you have the damage, the hesitation of the crack here. You have two branches here, but you see it will not, this is damage here. Here you see the butterfly stress at the crack tip here. And you will see branching, and then bifurcation. So one crack is winning here in the process. Okay. But what we need for these single crystals are 3D simulations. And there, since I am already late, I will show you only two pictures. What you see here is a crack. You have to imagine a sample with a flat surface. You have an initial crack, which is black, in fact, here. So you see the crack front, the initial crack front at the free surface. And what you see here are the propagation of the crack front, which was the sample was subjected to cyclic loading. And why there is such a complicated, and this is an experiment here. This is a measurement by X-ray tomography made in Grenoble, in the synchrotron facility. And what we have done is simulate this in crystal plasticity, where you see that the reason for these abrupt changes in the crack path is that there are grains in front of the crack, and the crack propagation is different depending on the orientation of the grains, this one or this one. The most critical one is this one, and you see here there is a crack propagation. It comes at the grain boundary, and then it crosses. There is hesitation, again, a few cycles, and then you have a propagation. And this we have tried to model. I must say this is a tremendous effort from the computational and the modeling part, but I think this is something I have to tell in another lecture. Thank you very much.